Interference. Here we have the graph of a wave. It could be a water wave or a wave on a string, for instance. We've got displacement on the y-axis and position along the wave on the x-axis. If this wave is joined by another wave, the two add together to produce a wave something like this, with the peak twice as high and the trough twice as low. This effect is known as superposition, as when two waves meet, the total displacement is the sum of the individual displacements. These two waves meet in phase, and so they constructively interfere, producing higher peaks and lower troughs. If the two waves met like this, completely out of phase, they would destructively interfere, and the sum of these waves would just follow the x-axis. In reality, these two situations and anywhere between them would be possible. What we have here is two sources producing water waves. We have the source producing blue water waves travelling out from here, and here the source producing red water waves. If the two sources are what we call coherent, meaning they have the same frequency and therefore the same wavelength, and a constant phase difference, which could be zero, the interference will occur at fixed points. If we look along this line, we see that here a peak from the blue, represented by the blue line, meets a peak from the red. The same happens here and here and here. We can join these points up using a line, and along this line we would get constructive interference. This means the water surface would go extra high and extra low along the line. We can show other lines where this will occur. So for instance, along this line we have peak meeting peak, peak meeting peak, and so on. Likewise along this line. So we can say that the lines show points of constructive interference. There is a whole number of wavelengths path difference from each source. To show what we mean by that, I'll mark this as a point of constructive interference, and you can see this is 1, 2, 3, 4 wavelengths from the red source, and 1, 2, 3, 4, 5, 6, 7 wavelengths from the blue source. We could do the same for any of the points where the lines cross. We will find there a whole number of wavelengths from the red source and a whole number of wavelengths from the blue source, as all the points on the lines are. And so there will be a complete number of wavelengths path difference from one to the other. If we now look at what happens between the black lines, we see that, for instance, here there is a peak of the blue halfway between peaks of the red, and therefore at a trough of the red. So we'll get destructive interference here. At this point, a peak of the red is halfway between peaks of the blue, and therefore here we'll have a trough from the blue wave and destructive interference. So there will be very little water disturbance along this line. And we can say that in between the black lines are points of destructive interference. There is an odd number of half wavelengths path difference from each source at these points. So looking at this point of destructive interference, for example, we find it is 1, 2, 3, 4, 5, 6 wavelengths from the red source, and 1, 2, 3, 4 and a half wavelengths from the blue source. It is this extra half a wavelength that is important and leads to the destructive interference.